Hello and welcome to Week 6 lectures. This week we'll cover some more topics dealing with analysis of discrete and count data in the form of tables. So we'll take a look at chi-square tests for homogeneity and independence, and then what's called Fish's exact test. So the idea here is we've got data that is categorized or in groups, and we have a table of some kind. These are nominal variables, or categorical, or ordinal, usually nominal when we're looking at, say, tables of this kind. So instead of what we've got is, on every observation we've got counts, and these are generally summarized in tables or some other way, but presented usually in what's called a contingency table. So this is essentially a 2x2 table, or maybe more as well. We can summarize this in various ways as counts and frequencies. We can also draw graphs, bar charts, or whatever else. What we're after here is a few things. In the two-way tables with two categorical variables, which we can present as a contingency table, one variable can be thought of as a response, and the other one can be thought of as levels of some kind of treatment. And so what we're after here is to know if the proportions of the response variables is the same for all levels of the other variable. The example we'll take a look at to start off with here is this survival data on the Titanic. So the idea here is, the question here is the survival status the same for all particular types of the passengers? So they're either crew or first class or second class or third class. We have the data here and the status of whether they're alive or dead. So we want to know whether the status alive or dead is the same for all classes of passengers. So here's the data frame. You can see how we went to this in here. We've got the counts in one column essentially, and the status here we generated here 2 to 4. Labels as alive or dead, and so the GL here will give you 2 levels, but repeated 4 times. So alive 4 times and dead 4 times. And the class here is with the labels here for the type, which is crew, first class, second and third. So have a look at that code and see whether you can understand the thing and see whether it produces for you the data. So here's the bar plots of this data here. The various classes of the passengers and their status alive or dead. By looking at this, it's pretty clear that it looks like if you look at the crew, more of them died and more of the third class passengers died. But the first and second class, by and large, the number that died and alive are about the same. In fact, more of the first class was alive and not so many of the second. The question we're going to ask here is this difference significant? So this we can do by what's called this chi-square test for homogeneity. And what we can do here is, what we've done here is we've actually converted all the numbers into probability by dividing by the total. So you can see this here is 1 because we divide by the total here. And so we have probabilities over here. The question we're asking here is that, well, we essentially call this a joint distribution. So we've got the joint distribution of probabilities for the status of passenger, which is the type of passenger, and whether they are alive or dead here. And the question we're going to ask is, are these two probabilities the same of being alive or dead for each kind of passenger? By looking at the numbers in the table, it doesn't look like that. Looks like probability of dying for a crew is much larger, and for a first class passenger maybe about the same. The same here for third class passengers. Probability of dying seems much larger here. But we really want to take a look to see whether this is a significant difference. Now these probabilities here again are found by the sum over here divided by the total, but of course you can see that the sums here should all be across columns here. Down the column they should all add up, and the sums here as well across the rows. This is probably just a rounding error over here, but that should, in the end should all add to 1 in the end. So how do we go around doing this test? Well, we've got the table here prepared in R. Next times is the command we use here. It's the count against status. So you can learn all these R commands as we go through here, and you can see we've got here the particular table that we've got. And by taking a look at, it says column sum of the table, divide everything here by the column sum. The column sums comes to us as we've got there. We divide the, says, have a look at how this sweep command works very carefully. You can look at the syntax and how it works online. But the way it does is, it takes a look at this table, as we know that 1 stands for the rows and 2 stands for the columns. So it goes across the columns, and this last thing is the function it actually performs. It divides every column by the column sum over here. And that gives us here probabilities for the columns, so that you'll find the columns here now add to 1. So this, the idea here was, we fix the column totals and view the survival rates across the groups. So we can see the survival rates here. For the crew, more of them die. Probability of dying here with the crew is much larger. The second and first class, more of them seem to survive. And of course the third class, there's quite a bit of difference here as well, the second and third class. And this is a bar plot of that data, where we've got again looking at this, the probability of surviving is much lower for crew, much higher for first class, and then lower for the second and third class. But these are just graphs and ideas. We need to have some kind of test for significance here. So what we had was the conditional probabilities here of the survival given the kind of crew they had, the kind of passenger they were. What's the probability of survival conditional on being in the crew? Well, if you're crew, then probability of survival is 0.24, as we can see. So all these are probabilities, they all add to 1 down the rows, down the columns. The chi-squared test works this way. What we do is we work out, this essentially is saying that the survival probability is the same for all types of passengers. We want to work out, we want to test whether that's the case here. What we do here is calculate what's called this chi-squared test statistic. And the way it's done is the observed frequencies as we have in the tables, minus some way of calculating the expected frequencies, and the squaring that and then dividing by this expected frequency, then summing them all up. So the way it works is going to be for every cell we do this. The chi-squared test is, well, we don't think of this as one-sided or two-sided because it's a square, so everything becomes one-sided anyway in one sense. But because squaring turns everything across, it's not going to be a very the way the probability of the p-value here is going to be always in the tail, as we will see, and why it works that way. The degrees of freedom are calculated by the number of rows minus 1 times number of columns minus 1. Number of rows minus 1 times number of columns minus 1. Or if you look, number of categories, and then minus 1 again, number of groups minus 1. So number of rows minus 1 and number of columns minus 1 is the easy way. So let's see what this chi-squared distribution looks like. The parameter here for the chi-squared distribution is degrees of freedom. We saw that normal distribution has a mean and a variance. Binomial has n and p, and Fossil has a mean, and so on. Here for the chi-squared distribution, the degrees of freedom is the parameter. What we can do here is just plot this. So here are the plots for various degrees of freedom for 5, 10, 15, 20. You'll find as the degrees of freedom increase, the distribution becomes much more symmetric, and essentially it becomes much more close to normal. One thing you might not notice here, you might notice on the last one, is that the mean of the chi-squared distribution is equal to its degrees of freedom. So here the mean is 20. This is chi-squared 20. If you look at, say, 10, it seems to be a bit off because it's skewed. But still, that's the mean over there. And you look at, see, this is 10 over here. you look at, it's a bit skewed as I say, the green here is 15, and this mean is 15 is getting closer here to being the center of the distribution. But you can see that earlier on it's quite badly skewed. It's a skewed distribution, but it becomes more symmetric as the degrees of freedom increases. Assumptions here are that the data must be counts for categories of the categorical variables. The counts in each of the cells must be independent of each other, and we're really thinking here that we've picked these in some way in random form, but the last one of course is a sample size here, assumption that all the expected frequencies for every cell must be at least 5, bigger than 5. And we'll see how that works out as we go through. The null hypothesis is going to be that the survivors, distribution of survivors is the same across all core types. H1 says it's not the same. You can simply say H0 is false here if you wish. But there's no way of writing this, well, there are ways of writing this in a mathematical way, but we'd rather just write a thing in the word saying that the distribution of survivors is the same across all core types. So the assumptions here, the counted data condition is, well, these are counts of survivors. Independence assumption, survival status of each individual is independent of the other individuals. Randomization here is there's no reason to suspect bias in the recording of survival status, so there's no problem with actually doing that. There's no other generalizations planned here, so there's not much more to be said here. And the expected cell frequency counts, we'll see that as we calculate those. So this is how we calculate these things. The probabilities of alive and dead were calculated earlier. We've got those probabilities over here, but the calculations actually proceed a bit more simply. So the probabilities here, we can work out probability of being a crew in first class and all the rest of it. But the expected cell counts actually are calculated much more simply. All we do is we take a look at the row probability times row column probability times grand total. It actually works out to be a little bit simpler. It in fact works out to be row total times the corresponding column total divided by grand total. So we saw earlier what independence means. Independence here of being a crew and alive is going to be probability of being a crew times probability of being alive here. And then because we've got all together here, the grand total is 2201. Then if the probability of being a crew and alive is this probability, then the number we expect is going to be times the total number altogether. So this is the NP area. This is our N, the number of people or number of passengers altogether. And this is the probability of being a crew and being alive as well. So being a crew and being alive here times those probabilities because of independence, then times grand total. You can see that this actually cancels off. So I've got here the column total and row total multiplied upon the grand total. That's how each of these can be worked out. It's going to be the row total times column total times grand total. So here are the calculations for each of those. Again, I'm just going to knock off these things over here to make the calculations simpler. So while I've got probabilities and the independence ideas over there, really it becomes essentially this row total for each cell times the column total corresponding to that cell divided by the grand total. So look at this one here. The expected number in first class and alive will become first class and alive. The row, this is what I'm after, the expected number there. I'm going to have the row total times the column total, those two, and divided by grand total. So it's 711 times 325 over 2201. So you can look at all those calculations in the same way. Now, all the cell counts here, we said the expected number should be bigger than 5, and they're all much bigger than 5. So that last assumption is okay. I can set this up as a table. I've got the survival and group over here, so it's core alive, core dead, first class, second class, third class. and I've got the observed in each of those. The expected was calculated here, again as we said earlier, by the row total times column total divided by grand total. The formula for the chi-squared test is the observed minus expected. So there's my observed minus expected. Observed minus expected squared divided by expected. So this is how these numbers arise. You can check each of the numbers over here. This is observed minus expected squared, and you're going to divide by the expected, which is this number here. Then I add them all up. So my chi-squared observed here comes to 190.4011. Now the degrees of freedom for the chi-squared distribution is going to be the number of rows minus 1 times the number of columns minus 1. We have 2 rows, so it's 2 minus 1, and 4 columns, 4 minus 1. It comes to 3. Now the value we have for the chi-squared distribution here is 190. We said earlier that the mean for the chi-squared is equal to its degrees of freedom. So the mean here for this chi-squared that I have here, 3 degrees of freedom, would actually be 3. This is a very large number compared to 3. So I would expect that the p-value here will be small, and it is very small here. How does p-value work? Well, I'm again looking at a chi-squared distribution here. It looks like that. The p-value lies in the tail over here. P chi-squared gives me the probability for less than. I subtract that from 1. So this is the value for which I want the probability, and this is the degrees of freedom. And all we're doing here is putting a format over here. I want format for this to be what's called the scientific notation, to be exponential notation, and 2 digits only. So it's going to be 0 times 10 to the 0, essentially. So, in other words, it becomes very close to 0. You can see it's quite tiny here. Which means here that because the p-value is quite small, we reject the null hypothesis. So we say that the survival probabilities are not the same for all class of passengers. In fact, we can see that this first class and second class passengers had a greater survival rate than the third class and the crew as well. Later in the lectures, we'll take a look at how we do this in R and how we can take a look at more carefully. Once we decide that these things aren't homogeneous, we can decide by looking at essentially what we call residuals again, how we conclude this is the case here, that they have greater rates of survival than third-class passengers. So we'll see that in lectures later on Tuesday. 710 people who survived. And you will find, if I can go back for a slide or so, the total observed here is 2201. The total expected should also sum to 2201. You should find that's the case. So essentially, if I have found all the other entries over here, I can find the last entry by subtraction if I wish. Subtracting the sum of the previous ones from 2201. This becomes a nice little trick to use in smaller tables. And that's what's going on here. Likewise, again, this is again just a difference. Who total is expected minus alive in the crew taken off from the total. That will give you the expected dead in that particular cell. So that means that if I'm looking at this table here, once I've worked out the expected alive in here, I can find this by subtracting the expected from 885 and so on and so forth. I can make my calculations easier. That's just a trick that you can use. So have a look at that and see whether that makes sense. We'll cover this again in lectures. Now, degrees of freedom, we know how we calculate those. The next idea is similar. We've so far done the chi-squared test for homogeneity, saying the probability is the same for all groups for survival. Independence is a similar idea. In fact, exactly the same. If I say that the probability of survival is independent of class of passenger, that means they must all be the same. But sometimes you want to test for independence directly, and again, exactly the same idea works here. So here's an example. I've got this hepatitis C or no hepatitis C, and we've got the tattoo site here where there's a parlor or elsewhere or none, and we've got the question here of whether the incidence of hepatitis C and where this tattoo was actually done are independent, either related or not. So the mechanism is exactly the same. We set up the hypothesis in the same way, and we do the same kind of calculations, and the degrees of freedom are worked out in the same way. The same assumptions are required here. So the null hypothesis here will be that the tattoo status and hepatitis status are independent, and H1 says they are not independent, or again you can simply say that H0 is false. The steps are exactly the same. The expected cell counts are worked out the same way, so here probability wise we can work it out, but as I was saying earlier, all you need to do is it's cell column probability times row probability times grand total, or essentially column sum times row sum times divided by grand total. So this is the simple way of doing it. Instead of dealing with probabilities, which is how the mathematics works, as far as the mechanics is concerned, calculation actually works very much simpler like this: column total times row total divided by grand total for each of those. And check here that each of the expected frequencies must be bigger than 5. Now you find that this one isn't bigger than 5. And neither is this one. If I go back for a second to the table, you find some of the entries here a bit small, so that may be a concern. So this is a bit small, and maybe the expected won't be quite large enough there. So you can see 2 of the cells here have cell counts less than 5. If I was to go ahead and calculate the chi-squared test statistic anyway, as I have, I can do that in the same way. So it's observed minus expected squared, then divided by the expected, sum them all up, I get 57.9. Again, the observed frequencies and the expected frequencies add up to the same number. Here's chi-squared observed. My degrees of freedom here, I have 3 rows and 2 columns. So this comes to chi-squared 2. And my value here for the chi-squared observed value is quite large. We know the degrees of freedom for this chi-squared 2 distribution is 2. So the p-value will be quite small. It is quite small. So again here we reject the null hypothesis, and we conclude that these two variables, this is the incidence of a hep C and the place where the tattoo was actually done, are not independent. Now it says here, you notice the greatest discrepancy in the chi-squared calculations, and that comes by looking at the chi-squared calculations themselves. And the biggest problem here is if they were done in the parlor, that's where the biggest discrepancy is. And you can see what's going on here. The observed frequency of hep C is much larger than expected. We're expecting quite a low there, but it's actually much larger. So this is where the problem is. It seems that individuals who were tattooed in a tattoo parlor had the high incidence of hep C. But the one problem I was pointing out earlier is that we do have a problem here with a low cell count. The expected value, the expected frequency in this cell here is actually quite small. And the same with this one. So in fact, in this case, the assumptions of the chi-squared distribution don't hold. And so in such cases, what do we do? Well, there's several things we can do. One thing we can do is what's called Fisher's exact test, and that we'll cover in the next lecture. Before that, a brief note on how this chi-squared thing works out here is, for those who know more mathematics or are interested, is that the modeling the counts by a Poisson distribution. So there should be Poisson here. So y is Poisson mu. Then for large enough mu, if I take a look at mu bigger than or equal to 5, say, then if I standardize the y random variable, y minus the mean divided by its deviation, now we know the Poisson has the same mean and variance, so the square root of mu is the standard deviation. Then this z, the standardized random variable here, is approximately normal, not 1. And if I've got normal knot distributions Z1 to Zk, if I square them and add them up, I get a chi-squared K distribution. So I've got K of them added up, independent, and I get a chi-squared K distribution. This is how this arises. That's enough for this lecture. We'll take a look at Fisher's exact test in the next lecture. Thank you. Bye.